Hello friends, today we are going to calculate the consolidation settlement using MV, that is coefficient of volume compressibility. So we will take one example. In this example, let's have a square footing. This is the square footing which is embedded into the ground. This is the ground level, and the depth of the footing from ground level is 2 meter, and the size of the footing, a square footing, is 2 meter by 2 meter. So the width of the footing is going to be 2 meter. This square footing is carrying a load through the column QC equal to 400 kilonewton. That means the intensity of loading over the footing Q equal to QC divided by area of the footing, that is 400 divided by 4, so it becomes 100 kilopascal. Now it is resting over normally consolidated clay, and the groundwater table you can take it here, touching the ground level, and this normally consolidated clay is having the saturated unit weight as 20 kilonewton per cubic meter. So using MV, that is the coefficient of volume compressibility, calculate the consolidation settlement or settlement of this footing. So from basic we will go and see how to calculate it. You see, the intensity of loading is already known to you, that is the column load divided by area of the footing, and that's going to be 100 kP. Right. Now, what is the zone of influence? The zone of influence, as you know, the load is going to spread out, and let's say this is the zone of influence. There is 2 vertical, 1 horizontal. Load is going to spread like this, and the zone of influence, this is very important, in which the load will be felt. Load is going to compress the soil and leading to rearrangement of particle, leading to settlement of the footing. So this zone of influence, normally we take from shear criteria 2 times the width of the footing, but you can calculate it. Let's say the zone of influence is where the intensity of loading which is acting at the base of the footing is going to decrease and becomes almost 10% of the intensity of this loading. So Q is 100 kilopascal. Therefore, 10% means 0.1 times Q will be 10 kilopascal. So where the due to this column loading, this effective vertical pressure increase is going to be only 10 kilopascal. In that, the uh, value of Z will be zone of influence. So you can find Z, which will be zone of influence. So you know that delta sigma prime, the increase in vertical stress or vertical pressure is given as this Q, that is the intensity of loading multiplied by the area of the footing divided by B, the width of the footing. At this depth, there is going to be the width of the footing, if this is the zone of influence, and two vertical, one horizontal. This will be Z by 2 this side. This will be beyond this. This is also going to be Z by 2. So B plus Z whole square. So the load is going to spread over an area of B plus Z square, where Z is the zone of influence, where the intensity of loading becomes 10% of the intensity of loading at the base of the footing. So now you know this uh, increase in effective vertical pressure, delta sigma prime, is 0.1 times Q. Therefore, 0.1 times Q equal to Q into area of the footing. You already know that the area of the footing is going to be 2 into 2, that is 4 square meter. It is a square footing, divided by B, width of the footing is 2 meter. So 2 plus Z whole square, isn't it? So now the value of 0.1 times Q is already known to you. It is 10, and so this is 10. The intensity of loading Q at the base of the footing due to column load is 100 into 4 divided by 2 plus Z whole square. Right? Therefore, we can write 2 plus Z is going to be equal to 0, 0 goes cancel. So it becomes under root 40. So we can calculate it. 2 plus Z equal to under root 40. So under root 40 equal to, this becomes 6.32 equal to 6.32. Therefore, the depth of influence equal to 4.32 meter. So this value Z is going to be 4.32. So let's take total Z equal to 4.5 meter. Now, if you see the IS code, To calculate the consolidation settlement, IS 8009 Part 1, it deals with the consolidation settlement of a footing resting over the saturated clay. Naturally, you know that you will have to divide this zone of influence into minimum 3 layers. So you will have to divide it into minimum 3 layers. So let's divide it. So if total depth is going to be 4.5, 3 layers means each layer will be of 1.5 meter. So the first layer, the second layer, and the third layer. This is the first layer from the base of the footing up to here. This will be first layer H1 will be 1.5 meter. The second layer here H2 will be 1.5 meter. And this is the third layer where H3 will be also 1.5 meter. So we have got 3 layers. So all the 3 layers, we can write it that so we can write it H1, the layer 1 thickness of the clay is 1.5 meter equal to H2, the layer of clay thickness for layer 2 equal to H3, the thickness of clay layer 3. So total, therefore, H equal to H1 plus H2 plus H3 becomes 4.5 meter. So the zone of influence has been divided into 3 parts. Now, you have to use MV to calculate. Using MV, you have to calculate the consolidation settlement of this footing. So if you consider layer 1, this is the layer 1 where H1 is going to be 1.5 meter. It is uniform clay and fully saturated. Therefore, we will have to find out SC1. The consolidation settlement of first layer will be the coefficient of volume compressibility of layer 1 into the average increase in effective pressure multiplied by H1. Now, how will you find out the increase in pressure? Here at the base of the footing, you know that the intensity of loading is 100 kilopascal or capital Q equal to 400 kilonewton. So that will help you. So what you will have to do it at the midpoint of layer 1, say A, calculate the increase in effective pressure delta sigma prime due to this loading. This will be equal to the intensity of loading at the base level multiplied by the area of the footing, that is B square, upon at the midpoint. Let's say the midpoint is A. This is the midpoint. So at the midpoint, what is the depth? At the midpoint, it is 1.5 by 2. So this is going to be 0.75 meter. So this will be B plus Z1. Let's say this is the midpoint is Z1 whole square, where Z1 equal to 0.75 meter. This is the height at the midpoint. So this is for the layer 1. Therefore, delta sigma 1 prime is 100 multiplied by 4 divided by 2 plus 0.75 whole square. So this is the increase in pressure. Let us calculate this. Now, if you calculate this, this becomes equal to 400 divided by 2.75 square is equal to 52.89 kilopascal. This is delta sigma 1 prime. Now, what is the effective overburden pressure? The effective overburden pressure sigma naught prime at the midpoint for layer 1 has to be calculated. Now you know the saturated unit weight is given to you as 20, but there is water table. So minus 9.81. This is the submerged unit weight multiplied by the point 1, point A. This A is at a distance of 0.75 plus 2. So it is 2.75. So you can calculate this. So this becomes 10.19 multiplied by 2.75. This gives you 28.02 kPa. Right? So the pressure increases from this to this. Before external loading, the effective overburden pressure was only 28.02. And after loading, after having the footing at the site and applying the load of 400 kilonewton through the column to the footing, the pressure at the midpoint of layer 1 increased from 28 to 52.89. So this is the increase in pressure. This pressure is going to, the pressure has, the total pressure, therefore, the increase in pressure is up to this. So total pressure, therefore, the sigma naught prime plus delta sigma prime of layer 1 is 28.02 0.02 plus 52.89. So it becomes 80.91 kilopascal. So your original pressure before construction, it was only 28 kilopascal. Now, after construction, this is after construction or after placing the footing, the load increased from 28 to 80.91, almost 81. So you will have to perform the one-dimensional consolidation test, because MV is not unique like CC. It is for a particular pressure range. So you should increase the pressure from 28 to 80.91 in one-dimensional consolidation test. So perform 1D consolidation test. And here it is uniform clay, so it is going to be one way drainage, not double drainage, and increase the pressure from 28 kilopascal to 28 kilopascal and find out the value of MV1 by knowing what is the change in void ratio for the pressure increase from this range to this range, isn't it? So already if you collect the undisturbed sample, this was already subjected to this, and when you increase it by this, then it becomes this pressure. So for this pressure range, you can find it out divided by what is the sample thickness, and that will give you MV1 value. Let's say this value is 1 into 10 raised to power minus 3 meters square per kilo Newton. So you have the value of, for layer 1, the value of MV1 is known to you from one-dimensional consolidation test as 1 into 10 raised to minus 3 meters square per kilo Newton. This you know it. And therefore, if I want to calculate this SC1 now, so how will you calculate this SC1? I know MV1. I know what is the increase in pressure. The increase in pressure at the midpoint is already known to be, this is going to be delta sigma 1 prime, and that has become 52.89. So this is known, this is also known, 52.89, and the thickness of layer 1 is already known to me as 1.5 meter, and therefore I am in a position to calculate the consolidation settlement using MV. So let us calculate this. I hope you understand the difference between MV1 and CC. CC has got one unique value, whereas this is a specific to pressure range MV. So here, if I substitute the value, this is equal to 1 into 10 raised to minus 3 multiplied by delta sigma 1. This is given to you, MV1. Then delta sigma 1 is already you have calculated as 52.89 89. So 52.89 kilopascal into 1.5 meter. So if you simplify, if you calculate it, let us calculate and get the value. This gives me 0.079 meter. So I go, no, the value of SC1. Similarly, I have to go to layer 2. This is my layer 2. This is my layer 2 now. So go to layer 2 now. So if you go to layer 2, H2 is going to be 1.5 meter and SC2 will be MV2 multiplied by delta sigma 2 prime into H2. Now, I have already calculated, I will write it here, SC1 equal to 0.079 meter, right? Now, MV2, I have collected the sample from this layer uh, uh, and I can find out the value of MV2 by knowing the change in void ratio while performing the 1D consolidation test, and how to find out this delta sigma 2 prime. So delta sigma 2 prime is very simple. We know it is Q, that is 100 into the area of the footing, that is 4, divided by, now at the midpoint of layer 2, that is at B, this is going to be 1.5 plus 0.75. So the vertical depth is going to be 1.5 plus 0.75, that is 2.25. So Z2 equal to 2.25. So it will be B plus Z2 whole square, where Z2 is going to be 2.75 meter. So this becomes equal to B is 2 meter, Z2 2.75 meter. So 2 plus 2, that is 4.75 meter whole square. So we can calculate 400 divided by 4.75 square. This is 17.73 kilopascal. So delta sigma 2 prime is known to be. So I know delta sigma 2 prime now. This is known. MV2 is known from one-dimensional consolidation test. So MV2 is known to me. So MV2 is 0.7 into 10 raised to minus 3 meter square per kilonewton, where MV2 is calculated the same way. What is the change in void ratio for the increase in pressure for the pressure range? Now, what is the effective overburden pressure at point B? That we can calculated. So the effective overburden pressure sigma naught prime for at the midpoint of layer 2, that is at B, will be how much? This is going to be 2.25 plus 2, that is 4.25. So 4.25, this is 2 meter, this is 1.5 meter and 0.75 meter. That becomes 4.25 meter into the unit weight is 20 minus it is submerged 9.81, and therefore 10.19 multiplied by 4.25, this gives you 43. So 43.3 kilopascal. Therefore, sigma naught 2 prime plus delta sigma 2 prime becomes 43.3 plus 17.73. There is 61.03 kilopascal. So a pressure range from this to this, 43 to 61, perform one-dimensional consolidation test and find out by usual way the change in void ratio recorded in the dial gauge with the help of dial gauge, and the usual procedure. You can find out what is the change in thickness and what is the change in void ratio. What is the total increase in pressure is already known to you. The total increase in pressure is calculated here. This is the total increase in pressure, and the thickness of the sample is known to you, and therefore you can calculate MV2, and this has been given to you as 0.7 into 10 raised to minus 3 meters square per kilonewton. So having got this, I can now calculate SC2. So SC2 therefore can be calculated as 0.7 10 raised to minus 3 multiplied by delta sigma 2 prime, that is 17.73 kilopascal, multiplied by the thickness of the second layer is also 1.5 meter. So if you calculate this, seventy point three into 0.7 into 10 raised to minus 3 equal to 0.018. So SC2 equal to 0.018 meter. So you have calculated SC2 equal to 0.018 meter, right? Similarly, go to layer 3 and calculate the value for layer 3. So I will be calculating for layer 3. So for layer 3, you know S3 is 1.5 meter and SC3 will be MV3 multiplied by delta sigma 3 prime into H3. Now, MV3 For the pressure range, it has been performed one-dimensional consolidation test, and it was found out to be 0.5 into 10 raised to minus 3 meters square per kilonewton. So this is known to you from one-dimensional consolidation test. Now, how will you find out delta sigma 3 prime? Now, due to the external loading, the intensity of loading into the area of the footing divided by B plus Z3 whole square. Let us take at the center of this layer 3 a point C. So at C, it will be calculated as 100 into 4, B will be 2, and Z3 will be 1.5 plus, that is 3.75. So 3.75 whole square. So if you calculate this, you will be getting 12.09 kilopascal. Almost this was 100. Now you are getting 12 at the midpoint of layer 3, almost 10%. That is called zone of influence. When the pressure decreases as you go down from the base of the footing and become almost 10%, that is called the zone of influence. So 10% of Q. Here Q is 100. It has come down to 12. So you have got this. Now, this what is the overburden pressure effective for layer 3 at C? You see 2 meter, there is 3, 5 meter, 5.75 meter. C is at a depth of 5.75 meter, then 20 minus 9.81. This becomes equal to 10.19 multiplied by 5.75 equal to 58.59. 58.59 kilopascal. So the effective overburden pressure has increased continuously as you go down, but the increase in pressure post loading after construction of the footing is going to decrease, and there is the increase in pressure. And now MB3 is known to me. Therefore, I can calculate the consolidation settlement of the third layer now. MB3 is 0.5 into 10 raised to minus 3 multiplied by delta sigma 3 is 12.09. That is the increase in pressure over the existing overburden pressure into 1.5 meter. So if I calculate this, so I get it there is 0.0090 meter. Therefore, total consolidation settlement SC equal to SC1 plus SC2 plus SC3. Therefore, if you calculate it, 0.018, 0.079, it is 0.106 meter. There is the total consolidation settlement if you are going to use MB. But MB doesn't have any unique value. For layer 1, it is this value. For layer 2, this is this value because it is related with the pressure range, and therefore you will have to calculate like this. So with this example, I have been able to make this point, drive this point home to your mind that what is the difference between CC and MB and how to calculate the consolidation settlement using coefficient of volume compressibility. Thank you very much.